For differential amplifier, the constant current supply for the emitter is fundamental to the appropriate working of the differential amplifier. The simple arrangement which we exhibited in the basic circuit consisting of the resistance R e and the battery, the DC source V E E, that does not form a very good constant current source, for the simple reason that Norton's equivalent of that is having the source resistance R e, and the current source should have a very high impedance. R e cannot be very high because that will reduce the emitter current drastically. So, we can replace, a better arrangement is if we replace the arrangement of R e and V E E with a transistor. Now, transistor collector, as we know, is reverse bias, and that has much higher resistance than simple R e would exhibit, and therefore, that forms a better current source. So, the circuit under discussion was this, that resistance R e and battery V E E has been replaced by this transistor circuit. Now, here there are two resistances R 1 and R 2, a voltage divider bias is being used, and here we can Thevenize this circuit, and Thevenizing the biasing network for Q 3, Thevenizing biasing network of Q 3, that is this transistor Q 3, you know simple rules of the Thevenin's theorem, T H Thevenized voltage is whatever is the voltage across this. So, the current will be V E E by R 1 plus R 2, and that current when passes through R 1 gives a voltage, and that is Thevenin's voltage. This is that, and the emitter current, as we have done several times when we were talking about bipolar transistor, the emitter current I e is V T H, that is this voltage which we calculate, minus V E by resistance R e, this resistance R e. So, this is the emitter current, and this will be much more constant than the earlier one, just the current which will be flowing by the resistance R 3 with the R e with battery V E E. And so, the tail current I t is half of this is I e 3, that is this current and this current. I c 3 is equal to I e 3, because in bipolar transistor emitter current and collector current are very close to each other. So, this is half of I e 3. Now, in this arrangement, which is quite very widely used, we have taken care for one factor, and that is of the current source. This current source will have much higher impedance, source resistance in comparison to the previous arrangement, but still there can be some variations because of current, this this voltage VBE, this voltage VBE, this is temperature dependent. 2.5 millivolt per degree it falls. So, this variation will cause, if this input voltage VBE varies, and that will vary the IB of this transistor, and hence IE will depend because of temperature variations. And so, one of the better than this arrangement is if we replace this resistance R1 with 2 diodes. So, this is the diode compensation technique, and the circuit is these are the two diodes D1 and D2. So, the voltage here, this will be 2 VD, where VD is voltage drop across one diode, and this is this resistance here, resistance R1 is replaced by 2 diodes. Important thing is that the characteristics of emitter base junction of the transistor Q3, they have the same characteristics as these diodes. Diodes we have chosen not any diode, but the diodes which have similar characteristics, identical characteristics as the emitter base junction of the transistor. So, any variation which will occur here, that will be compensated by the because this voltage across this VD will also be temperature dependent, and they will change to compensate the changes, and hence here it can be shown, this circuit can be analyzed, that IE3 is equal to VD by RE. This is R2, this is grounded here, the voltage drop is VBE. So, this is this, and because this has been derived from 2 VD minus VE. For example, I could have written another expression earlier than this as 2 VD minus VBE, this voltage minus this voltage by RE. But because they have identical characteristics, the base emitter junction diode and these diodes, so VD is equal to VBE, and when we use that, then we get this expression. And further it can be shown that how to choose the value of R2 for this. This is VEE minus the voltage, which is normally 1.4 volts by IE3. IE3 is here, this resistance can be calculated, and this normally comes in the range of 100 to 200 ohms. So, this way this is one of the best constant current source which takes care of two parameters. The source resistance, constant current source resistance, has very high source resistance in this circuit, and it also takes care for the temperature variation of this voltage VBE, and so this is one of the best. So, this was the constant current source, and what are the various options which we have. Now, we define another very important characteristic by which we differentiate between, this is one of the characteristics between among different differential amplifiers, and this is, the parameter is common mode rejection ratio. Common mode rejection ratio, CMRR. This is also called CMRR ratio, common mode rejection ratio. Right in the beginning we have said that any voltage which will be common to both inputs, that will be totally rejected, totally 100% rejected at the output. Any circuit we take, either this circuit, here also any in the differential mode, when we take the output here from two collectors, then whatever signal is common to both, we said it is totally rejected, it is absent in the output. So, whether this circuit or this circuit, that does not make a difference. Now, this is a ideal situation. This assumes that the two halves Q1 and Q2, these are 100% identical. This is true that, as I made a statement in the beginning, that normally differential amplifiers are fabricated as IC on a single chip, and the process of fabrication is the gas diffusion for introducing N and P impurities to make these transistors and resistors and all that. So, the process is very systematic and computer controlled. In spite of all that, some differences may occur, and they do, between the two transistors characteristics, and this compensation is not 100%. That means, any signal which is common to both is 100% absent is an ideal situation. It is not the practical thing. Practically, yes, well designed differential amplifiers, this will be largely absent. Any signal common to both will be largely absent, but a little bit, few percent may still be there. So, this property of the differential amplifier, that to what degree it eliminates any signal which is common to both inputs, that is measured by this ratio, common mode rejection ratio. I hope I have made the point clear. Common mode rejection ratio, CMRR, is a parameter which is a measure of the ability of the differential amplifier, which states that to what extent the common signal common to both inputs is absent in the output, and this is defined as CMRR, common mode rejection ratio, is defined as the ratio of the magnitude of differential gain and magnitude of gain in CM, common mode. So, that is where AD is differential gain, gain of the differential amplifier, gain of differential amplifier in differential mode. So, this is called commonly differential gain, differential voltage gain, or simply differential gain, and this is this ACM, this is common mode gain, common mode gain. So, this ratio gives CMRR, and normally CM, the common mode rejection ratio, is expressed in decibels, in dBs, and then CMRR becomes, this is equal to 20 log base 10 AD by ACM. This is in dBs. Common mode rejection ratio in dBs. Now, how to measure this? These two gains we have to measure. So, let us take the basic circuit. This was the circuit which we have been talking, the basic circuit. This was VI1, VI2, RC, RC, and this is V out, C1, C2, Q1 and Q2. So, we give two signals, they differ slightly, say for example 0.5 millivolt, and then we measure this output. So, the difference of the two output is supposed to be A d Vi1 minus Vi2, or this is in differential mode. So, Vo is Ad into Vid, and so we can measure Ad as V out by Vi difference. This is the way we can measure the differential gain. We apply two signals, two input signals slightly differing in magnitude by say 0.5 or 1 millivolt, and we measure the output, and from this expression we can find out the differential gain. And the common mode gain we can measure by supplying the same signal to both. For example, here i.e. here the two inputs are shorted and we feed with respect to, all voltages are with respect to ground, what we measure here is with respect to each other of course, but this we give VI1 which will be same as VI2 and which is same as VICM common mode. Here we apply a signal which will be common to both and we measure the output here RC plus VCC, we measure the output here. We can get, these are direct coupled amplifiers and hence they will respond to even DC. So, we can use DC voltages, two DC voltages in the first case differing slightly, we measure that difference and we measure the output in the from the two collectors. In this case also we apply the same signal, we short the two inputs and of Q1 and Q2 and apply the same input to both. So, this is input in common mode and we measure the output and ACM will be equal to VO by VICM common mode whatever signal we give. Now, ideally for the common mode V0 should be 0. So, ideally this gain for common mode will be 0 and then according to this definition common mode rejection ratio ideally is infinity. CMRR approaching infinity ideally. But with the presently available advanced technologies, this CMRR it is of the order of 70 to 80 dBs, which is also very high, and so this CMRR higher it is better it is, and practically this goes up to 80, 85, 90 dBs, which is very high value. So, this way we have done with the differential amplifier. Differential amplifiers, they form the first stage of operational amplifiers which we are going to study now. So, we take up now operational amplifiers. Operational amplifiers in brief and most commonly they are called op-amps. From operational amplifier we call them popularly as op-amps. Op-amp today is a very important component in every digital and analog system. You will hardly find a system in which op-amps have not been used, they are very widely used. There are 2000 different kinds of op-amps, more than 2000 different types. $2,000 and more different types of op-amps are now commercially available. They are very inexpensive and why so such a large number? Because different applications will require different characteristics. So, to meet those requirements these operational amplifiers have been developed with different characteristics. Now, what are op-amps? Op-amps are operational amplifiers are very high gain, multi-stage, direct coupled, direct coupled amplifiers. This is the main important points about operation amplifiers. What are operation amplifiers? Operation amplifiers are very high gain. How high? 10 to power 4, that is 10,000 and above. 100,000 is the gain, and this gain cannot be achieved from a single stage. It has to be multi-stage. So, it is a multi-stage amplifier. About multi-stage we have studied, and the major point I repeat, if we have two amplifiers, for example, they have a gain of 40 and 40 individually, when they are cascaded connected in series to form a multi-stage two-stage amplifier, then each stage has a gain AV equal to 40. So, the combined gain for the two stage when cascaded, the combined gain is the product of the two gains. So, the gain is 40 into 40, that means 1600 this way. So, this is a very high gain multi-stage direct coupled. Now, a word about coupling, though we have talked these points again, but here it is for the sake of revival of the concept, that what is the influence, what is the implication of this direct coupling. I said in differential amplifier that we can use sinusoidal signals or even DC voltages at input signals. So, this is possible only with direct coupled. There are RC coupled amplifiers, RC coupled, which we have studied, and for that gain versus frequency, this is frequency, this is voltage gain, and the response is like that. And this fall, this occurs because of low frequency cutoff, this occurs because of due to coupling and bypass capacitors. In direct coupling there is no bypass and coupling capacitor. So, the response for direct coupled, this is RC coupled, for direct coupled response is like this. This is gain, this is frequency, and this is 0 frequency. That means including DC, right from DC the gain, it will amplify the signals, and this is the response for a direct coupled . Operational amplifiers. The first operational amplifier, just to give in few lines the history of the development. Fairchild USA, a semiconductor company, this brought out the first operational amplifier in 1965, but it had certain drawbacks. Two major drawbacks were that the output may latch, then it will not vary with the input. In an amplifier, we expect that the output should vary in according to the inputs, except that they will be amplified. So, that was latching of the output was one problem, and oscillations, unwanted oscillations were second. But the same company Fairchild, after 3 years, that means around 1968, brought up the most widely used circuit, one of the most widely used op amps, which took care of these problems, and that was the real revolution. After that, of course, there are several countries, Motorola and Semiconductors Limited, and so many companies are making with their trade names the op amps. And now, as I said in the beginning, that there are roughly 2000 of them, different types, to meet all the requirements. Why it is called operation amplifier? This is called operation amplifier because besides a simple amplifying circuit, it can function as a summing circuit, as a summing, subtracting, differentiation, integration, and many other mathematical operations can be performed by this operational amplifier. So, because it is capable of performing many mathematical operations, it is called op amps. We will, when we go for the applications of op amps, we will study these quite a few of applications of these operational amplifiers. So, the most out of these 2000 different types, 741, this is the number of op amp. This is very widely used. It is a common purpose op amp for many lab experiments, and in many circuits this is very widely used, 741. So, we will take this as a model, but replacing by any other number, the basics which we are going to consider, they are not going to change. Operational amplifier is a multi-stage amplifier. So, the design is complicated, but I will demonstrate that what are the various stages that make a op amp and what are the function of those stages. So, op amp multi-stage amplifier, and the various stages are these. This is the input stage, which is a dual input. This is a differential amplifier, dual input balanced output differential amplifier, and obviously it will have two inputs, 1 and 2. This is non-inverting input and this is inverting input. We have talked about in great details that this is non-inverting. That means when we give any signal, then without changing its polarity, the output of this amplifier will be there. If it is a DC signal, if we give positive here because it is non-inverting input, at the output it will be positive. If we give a negative voltage, at the output it will be a amplified negative voltage. While here inverting input, if we give a AC signal like that, then at the output it will be inverse in phase. If we give a positive signal, it will appear as a negative, and if we give a negative signal, it will appear as positive, that it will change its phase. So, this is the input impedance. This is the input stage, and which is a dual input balanced output differential amplifier, and this stage provides high voltage gain, and remember that we said that differential amplifier has a very high input impedance. So, high input impedance. This is the first stage. Then this goes to the other stage, second stage. This is intermediate amplifying stage, intermediate amplifying stage. To further amplify the signal, and this is again normally a differential amplifier. Normally this is dual input unbalanced output differential amplifier. Now, I am sure you are familiar with the terminology dual input balanced output, and this is unbalanced output. That means from collector C2 of differential amplifier the output is taken. So, this provides, obviously it provides further amplification. Then it goes to the next stage, which is a emitter follower stage. Emitter follower stage, which is common collector amplifier. And what does it do? Because all this we are talking the block diagram, this is the block diagram of op-amp. The various stages of op-amp are these. So, if you remember, in unbalanced output differential amplifier, we said that because direct coupling is used, so the output will contain AC as well as DC voltages. So, it will have DC as well. So, this emitter follower, this takes care, this changes the level, the DC level. So, this stage shifts DC level. First I write due to unbalanced output, there is a DC component in output. So, it shifts DC, it shifts DC level. plus adds power. You remember ammeter follower we studied in details that there is a high voltage gain, there is no voltage gain, but there is a current gain. So, there is a power gain, because power gain is the product of current gain and voltage gain. So, it adds power to the signal. And then the last stage, this is the output stage, and this is a improved push-pull amplifier. Push-pull amplifier in a modified form, and modification is between two transistors which sit one over the other, there is a diode, and diode, it takes care that when one transistor conducts, other is off, and this is known as totem pole output. And so it raises voltage swing. And current supply capability of op-amp. So, and this is the output. Here this is output. So, these are the various stages of the op-amp, and there may be some variations, as I said, that there are very different, large number of different types of op-amps have been developed. So, some small variations are there, but basically these are the stages which form a op-amp. Op-amps are available as an integrated circuit, and the circuit symbol I draw. The circuit symbol is circuit symbol of op-amp. This is inverting input, and this is non-inverting. Two inputs, and this is the circuit symbol for a op-amp. All voltages are with respect to ground. And for biasing is assumed that it has been connected, but to simplify the circuit, it is not shown. So, actually the biasing is sometimes some people prefer to show this circuit like this as well, but this is the generally accepted circuit where it is implied that these biasings have been provided. The negative sign indicates inverting input, and plus sign that indicates non-inverting. So, these are the biasing. We have done this biasing that if we have a dual battery, or dual supply as usually it is called, For this we will need a dual supply. This VCC and VEE, these are two voltages, one is positive with respect to ground, the other is negative. For example, in the transistor, you remember this here, minus VEE, this is RE, this takes care for forward biasing, this is NPN transistor. So, this will forward bias the emitter junction and this will reverse bias the collector junction. So, dual power supply, that is with respect to ground, there are these voltages, this is VCC plus and this is minus VEE. This is the dual supply. There is no condition that both these voltages have to be always identical, but in practice they are used identical. 9 volts, 12 volts, 15 volts, this is the range in which VCC and VEE are used. Dual power supplies are available to supply these voltages, and normally the magnitude of VCC is identical to VEE. One is positive with respect to ground, other is negative. These are available very low cost, starting from 7-8 rupees for one op amp, maybe 10 rupees, and then the range goes. And the diagram, base diagram, pin diagram, this is like this. These are 8 pins, 1, 2, 3, 4, 5, 6, 7, 8. The output is here, V out, and the two inputs are here at 2, pin number 2 and 3. This is the inverting and this is the non-inverting. This is the connection for minus volt, that is for minus VEE, and this is the 7 number is for plus V, this is plus VCC, and these are offset. We will talk little later about that. Little adjustments are required for improving the performance of the op amp. So, this is positive offset null and this is negative offset null, and this is closed and NC, normally closed terminal. So, this is the 8 pins of the op amp. The base is available in which you insert the op amp, and you have to connect the negative supply at 4, positive supply at 7, and inputs at 2 and 3. Output is to be taken at 6, and 5 and 1 are for negative and positive offset null adjustments. So, this is about the base diagram, the pin diagram for the op amp. Now, important characteristics of op amp. Important characteristics of op amps. This is just what I have made statements already, but let me summarize that high voltage gain. High voltage gain, and the values 10 to power 4, 10 to power 5, this is the gain. And high input impedance, high input impedance. How high? They are 1 to 2 megohms, very high. And a small output impedance. These are high input impedance and low output impedance are the characteristics of a good voltage amplifier. So, a small output impedance, and this is around 100 ohms or so. Then large bandwidth, large bandwidth of several. Practically we will see that in open loop without feedback the bandwidth is very small because gain is very high, 10 to power 5. But without feedback op amps are rarely used. As we further move towards understanding various circuits, then we will see these points. And with feedback when we use, then several kilohertz is the bandwidth, which is sufficient for very large number of applications. And the next is large CMRR, common mode rejection ratio. Large common mode rejection ratio, and this is in the range because this is expressed in dBs. So, 70 to 80 dBs for most of the op amps. And one parameter which we have not yet discussed, and that is it has large slew rate. Large slew rate. We will talk about this point later, but because we are talking about the important characteristics of op amps, so I thought that I must mention at least. And this is, but we will talk, it's a distortion actually, and it puts a limit that if amplitudes are high, then frequency we cannot use very high, and so on. So, normally this is to the tune of 0.5 volts per microsecond slew rate. So, these are the characteristics. About this slew rate we will be talking later. Now, briefly I talk about the op amps in open loop, which is a rare use for op amps, and why it is rare, this also will become clear to you. So, op amps in open loop. That means without feedback. Without feedback. We will talk about this point in details, but one thing I just make clear, by open loop we mean this, that this is of course the voltages we have to supply, the output we will take, and here suppose we ground 1 and we give a small voltage here, and the gain for 741 op amp which we will be taking for our discussion, this voltage gain is 10 to power 5. So, this voltage will be multiplied by this quantity at the output. No matter how small is this voltage, it is 0.1 millivolt, even then it will become 100 volts at the output, but 100 volts are impossible. The voltage will saturate either with plus VCC or minus VE. So, and by saturation we mean that output will not vary with the input. We will talk about these points next time.